The title of this talk represents a dream. A dream that one day people won't have to worry about moving to Houston because of the next inevitable hurricane or flood. A dream that the plastics that are currently polluting our oceans can be broken down and recycled into useful products instead of killing marine life. And a dream that the extreme drought and famine that are plaguing large portions of our planet can be reversed, and the wars and humanitarian crises that result will become a thing of the past. For the past century, we have used fossil fuels for pretty much everything. It's really powered the engines of our societies, and not just our planes and not just our cars, but we use fossil fuels to make the fertilizers in which we grow our food and the medicines that we use to heal our sick and dying. Fossil fuels have truly revolutionized the modern world, but at what cost? Today, we're going to pump enough carbon dioxide into the atmosphere to be the heat equivalent of 400,000 Hiroshima-sized nuclear bombs. In those 3 seconds, that was 15 bombs. That can't possibly be a problem, right? If we do nothing, the sun will become our worst enemy. Since 2000, we've recorded 10 of the hottest years on record, and 2017 is on pace to shatter all previously set. But we do have reason to be optimistic. Solar technology has evolved to the point where we can provide off-the-scale electricity, off-the-grid electricity, to remote places like this Buddhist temple in Nepal. And the cost of solar technology has decreased to the point that we can begin to disrupt traditional fossil fuel markets. In my research, I'm not using light to make electricity. Rather, I'm trying to use light to make and break chemical bonds to make the food, medicine, and materials of tomorrow. I do that using nanotechnology. Small pieces of metal that are about 1,000,000 times smaller than the width of a human hair. On this scale, materials can have very interesting properties, like localized surface plasmon resonance. And don't worry, that's just a fancy way to say that when you hit metals with light, the electrons oscillate back and forth inside of the material. The problem is that not all nanoparticles are plasmonic. Every chemist's favorite tool, the periodic table, we can eliminate the materials, the elements that are not metallic, and then I'm going to color code all of the remaining elements based on how well they interact with light. As you see, we're only left with a few options of plasmonic materials, metals that will interact strongly with light, but the vast majority are either mediocre or very poor. The elements that are good at making and breaking chemical bonds, however, don't interact with light very strongly. So in my research, I combine the plasmonic and the catalytic metals into a single material to get the best of both worlds. We call this concept an antenna reactor nanoparticle. In this illustration, we have an aluminum nanocrystal decorated with palladium islands. The light hitting the larger aluminum particle increases the catalytic activity on the surface. This idea is highly modular. You can change the optical material to change what kind of light you'd like to absorb, and you can change the catalytic material to drive different types of chemical reactions that you're interested in. Today, I'm going to tell you 2 quick examples of how we can use antenna reactor nanoparticles to break down a few small molecules that are causing big problems. The most abundant greenhouse gases in our atmosphere are, of course, carbon dioxide, but also methane and nitrous oxide. The first story is about nitrous oxide. It's the 3rd most abundant greenhouse gas in the atmosphere, but it actually has a global warming potential 300 times greater than carbon dioxide on a molecule-per-molecule basis, and unfortunately, emissions are expected to double by 2050. Using aluminum decorated with iridium, shown here on the left, this is an actual electron microscope image, we can flow nitrous oxide over top of the catalyst surface and use an instrument called a mass spectrometer, which counts the number of molecules that hit the detector at a given second. Shown here is the high green baseline. When we turn the light on, that nitrous oxide begins to dip down, and we make oxygen and nitrogen gas, which actually make up about 99% of the air that we're all breathing at the moment. So relatively inert materials, turning a greenhouse gas into more or less synthetic air. The second example is a study that was led by my colleague Hussein Rabajazi in the back. He took aluminum nanocrystals decorated with copper oxide, and what he saw was that when he heats up these nanoparticles, they actually make 2 different products. Carbon dioxide sits on the surface, it interacts with hydrogen to make carbon monoxide, or it can react with hydrogen to make an equivalent of methane, which, as you might remember, is also a greenhouse gas. Taking these antenna reactor nanoparticles and now doing the reaction with light, you get a single product out. Reacting carbon dioxide makes only carbon monoxide. And now I get it. you're all probably saying, hold on a second, Dayne, carbon monoxide, that's pretty dangerous, right? But actually, carbon monoxide is a chemical precursor that can be used to make synthetic diesel fuels using other types of chemistry. So some have told me that this dream is impossible. There's no way you could make molecules using sunlight. But to them, I'd like to remind them that plants and bacteria have actually been doing this for millions and millions of years. So, we're here today, and hopefully in this short time that I've spent with you, I've convinced you that we can use the power of the sun to make the food, medicine, and materials of tomorrow. Thank you very much.